So in this lecture, we will learn how to analyze a continuous beam by strain energy method. Here we take the question asked in 2019 Anna University examination in December. So this is a propped cantilever with partly UDL loading and 6 meters span. So we have to analyze the propped cantilever beam and finally to draw the bending moment diagram. So we are going to solve this beam using Castiglio's method. So according to Castiglio's theorem of least work energy, that mathematically it is dou U by dou R is equal to 0. That means the total strain energy, derivative of the total strain energy with respect to the redundant reactive component is equal to minimum. Okay, that's what dou U by dou R is equal to 0. Therefore, first we have to find out which reaction is redundant and how many redundant reactions we have. That we have to determine first. Okay. So here, how many reactions we have? So the reactions are RA, MA, HA, because the support is fixed support, and RB. So we have 4 reactions, but how many equilibrium equations we have? Only 3. Therefore, the extra reactive component will be considered as redundant. Therefore, the structure is statically indeterminacy to singleton. Okay, so static indeterminacy ds is equal to total reactions minus available equilibrium equations, that is 3, is equal to 1. Therefore, one reaction is redundant, so only one extra condition is required to analyze the beam. So we can consider any one of these reactive components as redundant. Okay. So to compute easily, we consider this RB, that is a propped end reaction, as other redundant. Okay. So let RB be the redundant. Now from Castiglio's theorem of minimum strain energy, dou U by dou RB is equal to 0. Here 0 is given because there is no yielding of support. Suppose our support P is yielding by some 5 mm or something, then that time we have to substitute that value instead of this 0. Okay. And here we consider only strain energy due to bending, axial deformation or shear, and ignore. Therefore, total strain energy in bending U is equal to sigma of integral m squared divided by 2 EI into dx. Therefore, dou U by dou RB is equal to integrate this expression with respect to RB, then you will get 2 into m into dou mx by dou r divided by 2e. Okay, 2 to cancel, so we will get only a out. Into dx is equal to 0. So to solve this, it is better to form a shape, that is origin, span, limit, then mx and dou mx by dou r is the derivative. Okay. So first span we consider it from the tree, and that is the quadrant CP or BC, and we consider from section XX, okay, which is x distance from support. That's why we assign B as origin, and the limit of the span BC span is 0 to 3 meter. Therefore, consider the moment at XX section, which is equal to RB, is upward, therefore positive RB into X. So if you differentiate this RBX with respect to RB, then you will get only X plus X. Similarly, we consider so next span is CA. Here also we consider B as origin, that is, we are measuring distance from B. That's why X is from here to here. The section XX, okay, we put in the span CA or AC. Therefore, the limit of the span CA is equal to from here to here, but we are measuring from B. Therefore, here to here 3 meter. Therefore, our span CA starts at 3 meter to up to 6 meter. So 3 to 6. Okay. So, therefore, taking moment RB into X positive, but this is acting downward here, so negative. So minus 1 intensity of the UDL into this distance, okay, from C to the section. So over this PC is 3 meter, overall is X meter, therefore X minus 3 will be our UDL portion. So X minus 3 into X minus 3 divided by 2, okay, there is distance, which is mx, and differentiate this mx with respect to RB, will get X. Now we can substitute these values in the strain energy or characteristic use here. Therefore, we have two spans. First one is BC, which of 0 to 3 limits. Therefore, 0 to 3 into mx. This is mx into dou mx by dou r, plus this is the limit of next span CA, and this is our mx, this is our dou mx by dou r, which is equal to 0. There is no yielding of support B. Okay, there is no work done by the reaction RB at support B. That's what 0. Therefore, if you integrate, you will get RB is equal to 0.328 kilonewton. Now you can apply other equilibrium equations to find out the RA and M. So from sigma B is equal to 0, we will get RA, so which is equal to 2.67. kilo. From sigma ma is equal to 0, taking moment support A, we get the value of ma. See, everything we have studied in the previous semester, strength of the fields. Okay, how to take moment. So ma is equal to 2.532 kilonewton meter. Now the last part is to draw the bending moment diagram. But before drawing directly the bending moment diagram, we need some salient features of that bending moment. That is where the maximum bending moment occurs, where the bending moment is 0, that is the point of contraflexion. Everything we have to calculate, then only we can draw the bending moment diagram for this structure. Because these simple structures, therefore we have to write all those steps. So the given structure with reactions Ra, Ma is acting in anti-clockwise direction, and Ma already calculated as 2.532 kilonewton meter. Therefore, we can easily calculate MC, because MC from this side, okay, MC is equal to Rp into 3, producing positive moment. Okay, that is MC is equal to 0.984 kilonewton meter. And remember, Ma is the negative moment. Okay, Ma is the negative moment, MC is the positive. Because M is acting in anti-clockwise direction, MC is in the clockwise direction. Sorry, anti-clockwise direction also, but in the right hand side. Okay, and the MB, that is a property cantilever support, MB is equal to 0. To get maximum bending moment in span AC, because there we have the UDL loading. Therefore, we have to consider one section in AC and take the moment at section X and equate and differentiate Mx with respect to X and equating to 0 will give you the distance at which the moment will be maximum. Okay, this is section. So Mx is equal to Rb, the positive moment, Ra into X minus M is the negative moment, Ma in Ma, then again this UDL negative moment. So minus 1 into X into X squared. So for maximum, dou Mx by dou X is equal to 0. That is to get the distance at which we will get maximum. So Ra, Ma is constant, therefore no. Then minus X, okay, X squared, that is 2X into 2X by 2, therefore 2 to cancel. So X is equal to actually Ra, which is nothing but 2.672 meter from support E. Now substitute this X value in Mx expression, we will get the maximum at that point. So Ra is nothing but 2.612, X is nothing but again 2.612 minus Ma, okay, 2.532, then minus 2.612 into 2.612 divided by 2. So which is equal to 1.064 kilonewton. 1.0. How to find the point of contact where the moment is 0 in this span? Okay, because at support we have that is support A we have negative moment, but at mid span C we have a positive moment. Therefore, there is no somewhere moment is 0. Okay, in span AC. So that's why we have to find out the point of contraflexure in span AC. Okay, therefore we have to get moment at some section, at any section in AC. Already we have drawn the section and got the value. So equate that mx is equal to 0, so that we will get the value of the distance x at which the moment is equal to 0. Therefore 0 is equal to this mx expression. Therefore x is equal to the quadratic equation in x. Therefore x is equal to 1.23 bt. Okay. Now we will be in the position to draw the pending moment, because all the data we have to draw that. So this is the support moment, negative. Okay. So MC positive moment. Okay. MC here 0. The moment and the MC is 0.984 kN, but the maximum is somewhat inside, that is at 2.67, which is equal to 1.04, and the point of contraflexure is at 1.23 from support. So this is the PF.